So, crane stability. So, why are we talking about crane stability? Why are we still talking about crane stability? So, a brief Google of failures in the past 10, 20 years shows that we are still getting this wrong. There's a couple of examples here. These were both tower cranes, and there's been others that are kind of more structural issues, but there are various kind of failures that are happening in the country which show that there are still problems with this. So this is why we're still talking. So going over the basics, there's a few types of cranes that you should be considering, but the majority are, we're going to focus really on mobile cranes here. We've done various presentations on tower cranes before, but mobile cranes are probably more of the priority. So crawler cranes operate on tracks, so the pressure in general goes down through the tracks and onto the subgrade. Mobile cranes operate on outriggers, so when the crane is operating, the wheels are not on the ground, and the wheels are kind of, or the load is going down through the outriggers onto the subgrade. Also got three kind of types of tower cranes, so kind of ballasted tower cranes where there's just compression going through the foundations. Gravity tower cranes where you've got casting anchors, but the stability is maintained by the self weight of the foundation itself. And then pile tower cranes where the moments generated by the crane are kind of transferred via the piles, and both in compression and tension, and that's what provides stability to the crane. So a brief overview of roles. So the appointed person is the person who is responsible for the planning, coordinating and overseeing the lifting operations. They develop the lift plan and they select the correct lifting equipment, among other things. So the Syria Special Publication 131, which we'll reference a bit through this presentation, kind of gives you your kind of roles and responsibilities. And I've taken an excerpt of it there just to kind of indicate what's required. Where we come in as temporary works designers is we are provided with the loads from that crane when it's operating, and we carry out the checks on the kind of the subgrade or the structures that are loaded by the crane. And where required, especially during demolition projects, we might do work on working out the lift weights for structures. If it's not a specified lift weight, we'll carry out the assessments on the lift weight, where the central gravity is. And if the lift points are not kind of rated lift points, then the kind of structural assessment on that lift point. So main constraints. So what causes cranes to have issues, or what are your worries when planning your crane position? So I'm going to talk a lot about these, or more about these in more detail. So things to consider are adjacent to kind of things that would require third-party authorization. So the main one is Network Rail. They have specific requirements, which I'm going to go through. Adjacent structures, both, and kind of vegetation. So you get clashes both with the boom, and one that's often forgotten is the stays that come off the back while lifting. I've never had to deal with it, but there are restrictions when putting cranes up near airports. So that's something to be aware of in certain situations. Overhead cables, I've got a bit of information on how they can interface with, or should not interface with, cranes. Services and buried underground structures. So this is what, when you've got your outrigger loads on your kind of normally on road surfaces, what the kind of pressures or the allowable pressures onto surfaces are. There's the obvious risk of soft or poor ground, which most engineers are capable of assessing. It's a kind of, that's the more kind of fundamental thing that you'd need to deal with. One that's often forgotten is access and egress. So cranes, when traveling around site especially, have very large wheel loads, and the swept paths are quite complicated. So understanding how you're going to get your crane into site and how it's going to leave is important. And though not really controllable by the engineer, but weather also plays a part. It's nice not to plan all of your kind of crane operations for the winter, but it's not really in the temporary works engineer's control to deal with that. So Network Rail is the first one of those. So I've taken some screenshots from the CPA guidance here that kind of indicate what your collapse radius would be for certain cranes. So In general, you're looking for the length of the boom above ground, and that equals your collapse radius. Once you've got that, you then need to consider the length of the load that you're lifting, because if it's a long beam and the crane collapsed, then if that was orientated the wrong way, then that would get closer to the network rail line. And then they ensure that there is another 4-meter clearance zone beyond that kind of end of your item that you're lifting collapsing. If you're outside of that, perfect, that's the best situation to be, that your collapse radius is not near network rail. If that would overlap the network rail boundary, then there are requirements. So when it comes to mobile cranes, what you'll be doing is making sure that the crane is operating within 75% of its operating capacity. And to go beyond that, in general, you'll need to get a closure of the line. And also, on top of that reduction, you would need to factor up your outrigger loads. There's some double factoring happening here. You derate your crane, and then you factor up your outrigger load by 33%. So it'll provide quite a conservative foundation design for that crane, and the crane will be operating well within its capacity. Overhead cables. So the exclusion zone for overhead cables depends on the type of cables and kind of what you're operating. Also, should be noted that cables aren't static, especially on kind of tall pylons. They do sway in the wind, and they might sag more than they are in existing condition if they are running at very kind of max current when they heat up, or when they're loaded with ice, they can sag quite a lot more. I've got a screenshot there from the CPA guidance for lifting operations with excavators, which gives you some kind of minimum clearance zones. Obviously, the best thing is to be further away, so I would encourage to try to avoid operating adjacent to power lines, but where it cannot be avoided, that's some guidance on what to be looking out for. But the best situation is always not to be very close to them. So basement retaining walls. So again, I'm kind of referring a bit to the Syria guidance here. So they give a danger area in inverted commas of when you would require further engineering considerations. They look to retaining walls or adjacent to basements of 4 times the breadth of the outrigger pad, or 1.5 times the height of the retaining wall. So it gives some guidance on what is a kind of a safe place to put your crane where you don't need to provide further engineering consideration. To be fair, if you're right on that limit, I'd probably have a think about it anyway. But if you're within that limit, I would be kind of consulting an engineer to understand what the implications are on the structure from positioning your crane there. Slopes are pretty similar to basements. The distances are slightly different. So you're looking at 4 times the breadth of the outrigger, or the 2 times the height of the slope away from the base of the slope would be your safe distance that they consider. But with slopes, more than with basements, if you're on really poor ground, it's worth getting an assessment or a formal assessment on the effect of that prior to putting your crane there, because if that does fail, it will be quite a sudden failure and it may not be recoverable for the crane. It's not just going to sink a little bit. Services. So services are often one of the biggest unknowns with crane positions. If you're operating in most British cities, there will be numerous services. They in general won't be mapped particularly well, and there will be significant unknowns on the depths of services or the construction quality. On new sites, there are kind of design standards that should have been obeyed, and things like BS 9295 would give you an idea of what the allowable pressures onto those services are. In most situations, what you're relying on is a live load comparison to historic loadings, which doesn't completely eliminate the risk. It just kind of, if lorries are constantly going up and down that road, it gives you an idea of what that service would be subject to at the moment, and we can compare that to the pressure from the crane. Saying that, very brittle services such as cast iron water pipes, even at very small strains, can crack and can break and can cause water leaks. So there is a residual risk when putting cranes on above cast iron water mains that they may fail because of the nature of the cast iron pipes. Access egress. So I kind of touched on this. Cranes especially if they are in their kind of site travel mode, have some really quite significant wheel loads. I've just taken a screenshot from the technical data sheet for a Liebherr crane here. We can see there's lots of 19-ton axle loads. It can put some significant pressure if that is tracking next to any services or next to any retaining walls, and that needs to be considered. So you need to really think about your swept path of where your crane is going and what that will kind of interface with as it travels. So onto the geotechnical assessment. The first thing to do is to understand what the loads are onto your subgrade, and this is normally going to be through a few layers. So if you've got a mobile crane, it's not just in the direction of the lift that you've got your critical outrigger load. So obviously when it is lifting, you get the higher outrigger loads on the lifting side, but as soon as that weight has been dropped off, you've got the counterweight directly over the rear outriggers. They become the kind of critical, highly loaded case. And quite often when a crane is setting up and kind of slewing 360 with the counterweight over the outriggers, that can be the worst case, and it might not just be during lifting. And it's always good practice. We'd like to recommend, if possible, that the crane does slew 360 with the jib in, just to kind of bed in all the outriggers and ensure there is no movement when you're not lifting. With crawler cranes, you get a kind of a triangular load distribution under the tracks. So it's unlike with a mobile crane, when you've dropped your load off or before you've picked it up and the counterweight's over the rear, you get a triangular load towards the rear of the track. So both cases need to be considered. These loads we will quite often equate to an equivalent rectangular pressure for calculations, and that's an accepted way to do it. It's very similar to pile rigs. So types of outrigger mats. So assuming that your track or your outrigger is overstressing the ground without any outrigger mats, which is often the case, you would be looking at how to spread that load. And there's a number of different options. So the first and kind of one of the stiffer options is if you've got big steel mats, and a lot of cranes will come with some form of steel mats. And they should be allowed for. They provide pretty good load spread. They're obviously very stiff, so that helps a lot there in comparison to the ground. Timber mats, so traditional timber eccy mats, which will kind of provide pretty good load spread, and that can be assessed with how that will distribute the load over the ground. There's also plenty of different types of proprietary mats. There's both aluminium ones. There's kind of different types of kind of polymer mats as well. These are often more difficult to assess for a temporary works engineer because the data is not provided by the suppliers in some situations, or the data is incomplete. They may kind of almost inadvertently give you a maximum load, which the mats are incapable of spreading to that distance. So it's something to be aware of with proprietary mats, that even if they say that load, there's probably still a requirement to assess how flexible they are on soft ground. When you're coming to beneath those types of mats, then you've got your granular or your geogrid reinforced. So what you're looking to put there is some well compacted fill, which will generally spread the load at about 30 degrees through to the subgrade beneath, and kind of it also provides containment on granular and cohesive grounds. Geogrid reinforced, so the advantage of these is you can build up steeper batters and things if you are close to other site or other elements that require kind of protection, and you'll get better load spread from a geogrid reinforced mat. So maybe up to kind of 45, 50 degrees, depending on the type of geogrid and how tightly spaced they are. Also, if your crane is positioned on a concrete slab, that does provide load spread. I didn't bother to find a picture of a concrete slab because I kind of understood that people would understand how that actually works. So this caught my eye going through the special publication, which I found quite amusing. So it does note that a sheet of ply or a broken scaffold board doesn't provide a suitable foundation area. I think it's a good reminder that not everything is the same stiffness, and you really need to think about how stiff the mat is that you're putting down. So I like the kind of the gist of the quote. So when it comes to assessing how far that load would spread, so what we would generally use is the kind of a David Dewar method or something similar that looks at the stiffness of the crane mat in comparison to the stiffness of the ground, and how that kind of how far that mat would effectively spread the load. So if you've got a track in very soft ground, you would get pretty full load spread because the track of an excavator is comparatively stiff compared to the ground, as shown in the top surface. Whereas if an excavator was tracking on a concrete slab or something like that, then you would only get the crane, then you would only get load spread over the kind of short area underneath the crane. The same applies to outrigger pads, or outrigger mats. So if you've got a very stiff ground, kind of a working platform or a concrete slab, you don't get significant load spread from the outrigger mats. You don't just get the full load spread. And you need to kind of understand and calculate what that load spread would be over the length of the mats. David Dewar gives a nice way of calculating that. You look at your moment capacity of your mat, your shear capacity, and the allowable bearing pressure. And with those estimates, and they are estimate, well, the allowable ground bearing pressure is an estimate, you can then assess your effective length. Geotechnical assessment. So I didn't really want to go through how Eurocode 7 works or Tazagi. So you need to undertake a geotechnical assessment to make sure the ground is going to be suitable for the loads you're putting onto it. To do that, it may not be the top layer of ground that you're worried about. That might be quite good. It might be a road surface, but beneath that might be a more critical kind of stratum that would be loaded more by a crane than by kind of road vehicles because of the bulbs of pressure. The water table definitely needs to be considered because granular ground, when below the water table, will kind of provide a much lower capacity. You need to understand the load spread through the layers of the ground and the outrigger mats, as I've kind of touched on before. You do need to check the bearing capacity and then consider settlement. So global settlement may not be a huge issue, but differential settlement could definitely be an issue. So if some of your mats are on a hard surface and some of them are on a softer surface, if it's like half on a road, half on the site, then you really want to be thinking about what would be your differential settlement due to that crane. Is it going to tip at all? And just understand how that might affect things. So settlement should definitely be considered when looking at a crane. The bit from the Syria guide does note that, yeah, it could put more loads onto the jib. So even if you've not got a full geotechnical failure, that settlement could cause failure of other elements of the crane. Tower cranes in general have a maximum slope to prevent the kind of second order effects from the big counterweights being off-centered down the mast. So it's definitely worth having a think about and understanding when you're trying to place your crane. And the final bit on plate bearing tests. So quite often we'll get asked, can we just do a plate bearing test on the road or on a slab to justify that the ground is good to put your crane on it? So the kind of David Dewar puts a very good statement together, which clearly notes that it's not a very good idea. So the bulbs of pressure from a plate bearing test is not equivalent to a crane mat. A crane mat is much wider, and therefore you get a much deeper kind of pressure bulb, and you'll load the ground beneath that kind of harder top layer to a much higher pressure than a plate bearing test would. Even if your plate bearing test is going to 2-3 times the pressure, if it's only a 600 mil plate and you've got a 3 meter wide outrigger mat, it's just not comparable at all. So plate bearing tests are really good for assessing if your working platform is compacted correctly. They're not good for, or they're not a substitute for doing proper SI and understanding the geotechnical parameters beneath the kind of the road surface or the working platform surface. So I'd always steer away from those if possible to justify your crane positions. And there's some images there just showing kind of a 600 mil test that at the same level compared to a 1 meter wide track, you've got kind of 2.5 times the pressure from that 1.5 meter wide track at that depth. So I'm going to hand over to Rami now to run through the kind of quite a recent crane position we did over Echo Street in Manchester.
Thank you, Dave. So yeah, as mentioned, I'll briefly talk about a recent case study, which is Echo Street. And as you can see from the image on the right, it's very close by to Manchester Piccadilly Station. So this project is essentially the construction of some student accommodation buildings, which will be 3 towers of 16, 22, and 28 stories. Now, the principal contractor was Bowman and Kirkland, and we've had quite an extensive involvement within this project on the temporary work side of things, and this spans the entire project lifecycle. So from the very early works, such as the piling mat, right the way through to nearing practical completion now. And for today's case study, I will cover the dismantling of Tower Crane 1, which was positioned between the two larger blocks of the buildings. There were two tower cranes actually on site, both of which we designed the reinforced concrete foundations for, and TC1 was used to dismantle TC2 as it was taller, and now a 650-ton Liebherr mobile crane was used to dismantle TC1. And directly adjacent to the site on the south elevation, there's also an active network rail asset, which needed considering during this job. And this was done by derating the crane's capacity and factoring up the outrigger loads, as Dave mentioned previously. Now, next slide, please. The key considerations within the design stage was the proximity of the lifts to the network rail asset, which is why the risk classification for this job was Cat 3, and therefore Form C was also submitted as part of our design package for network rails approval. The checks that were carried out involved an assessment on the underground buried services. As you can see on the image in the bottom right, there was an extensive amount of services within the road and the pavement. Therefore, we had to ensure that the imposed pressures at this depth were within the safe working load of these services. Now, this was carried out as per a live load comparison, which Dave touched on before, where we compared the imposed pressures from a HGV wheel, which has proven to be okay, as we've got proof that they've run on that road before, and we compared that against our imposed pressures from the crane mats. The crane was also to be positioned directly next to two basements, which consisted of retaining walls, and these also required being assessed. And then a routine ground bearing assessment was also carried out to ensure that the underlying ground beneath the road and pavement level had sufficient capacity to withstand the large forces that we were going to be imposing on it. And finally, an assessment on the spreader mats was also carried out to determine the ability of the mats to withstand the point load from the outriggers and then to achieve the load spread area that we required for this assessment. So next slide, please. Once the design approach was established, we visited site and proposed some site investigation works to be carried out. Since the basements were mostly furnished, as seen in the bottom left image, we were unable to design a propping solution to support these retaining walls. So therefore, we had to carry out an intrusive investigation on the wall to determine the composition and the thicknesses, which allowed us to assess the masonry wall in its existing condition. And then trial pits were also carried out directly adjacent to the retaining wall on the public side. And as we suspected, that there was not. So before we did the site investigation works, we thought there may be some concrete retaining wall that was on the outer face of the masonry wall. However, this was not the case. The trial pits allowed us to confirm that the ground profile that we had interpreted from the nearby borehole logs and the ground were pretty consistent as well. So the proposal of this site investigation allowed us to eliminate many of the potential unknowns within the design stage and therefore produce an efficient and quite an accurate solution. So final design output, next slide please. The final design output was then to rotate the mats by around 30 degrees away from the front face of the retaining wall, and therefore this would transfer the load through the retaining wall in compression and through the return corner and along the wall panels, which is significantly better than loading the masonry in tension. Also, since the road surface was a hard standing, it would deflect significantly less than a Type 1 material, for example. So the load spread achieved through the mats would be much less as well. So to overcome this, we proposed extra steel mats and a 100 mil layer of sand to act as a compressible material and achieve the maximum load spread area possible. Next slide, please. And this was the crane all set up as per our provided drawings, and it took a while to rig it up as it had quite a lot of counterweights and a 23-meter fly jib, and it was assembled by help of an ancillary crane, which was positioned to the west of the crane, also along Granby Row. However, this was positioned far enough from any retaining walls. Yeah, these pictures show the jib of the tower crane being dismantled, lowered down, and then transported off site. The entire jib was brought down in one section, as you can see, and then put onto a back of a low loader and transferred away. Next slide, please. And once the jib and counterweights had been removed from the tower crane, the cab and the mast sections were the remaining lifts, and then they were also taken down sequentially. The entire job from the crane arrival to when it was transported away took around 3.5 days and was very successful. Quite a short turnaround, but yeah, went very well.